In this video, I will showcase a project called Snake Agent. This project is a snake game based on Q-learning for reinforcement learning, with the goal of teaching the agent how to maximize the score it obtains. So next, let me introduce the UI of the game. The UI part is not different from traditional snake games, and the episodes at the bottom refer to the number of training rounds, which is set to 1000 rounds here. Next, the game starts. I will focus on the first 2 rounds of every 100 rounds, as I have slowed it down the frame rate to 60 for these 2 rounds. The frame rate for the rest of the training is set to 2000. The game begins. In the first few rounds, the snake's movements are quite random because he has not learned anything yet. Its actions can be described as completely random. After a few rounds, the snake's behavior has noticeably changed, although its movements are still somewhat random and it turns to hit worse. There is indeed a trend toward the foot, indicating that it is learning. Accelerating training, it can be seen that the snake's behavior has changed significantly compared to the first round. The agent is more clearly moving toward the foot, although it still likes to hit worse. Continuing to accelerate, the agent is now mostly heading toward the foot, and the score has significantly improved. Continuing to accelerate, at this point in training, it is clear that the agent understanding of the game has greatly improved. It not only moves toward the foot, but also knows to avoid its own body, and worse, the score has reached 30 points, though it still occasionally hit worse. Continuing to accelerate, from these 2 rounds, it seems that the training effect has decreased. However, I don't believe this is the case because there is a parameter during training called the exploration rate, which sometimes forces the AI to make random moves. I think this is the cause. For example, if we go back to round 400, we can see that the score here has reached an astonishing 53 points, indicating that the training effect is indeed strengthening. Next, continue to accelerate. It seems there has been no significant progress. The chart also shows that after 500 rounds, the training effect has converged, so further training will no longer be displayed in video. Then we proceed with the test. The agent uses the previously trained Q table to perform an action. It can be seen that the agent's behavior is very smooth, and in the end, it also reaches at a 48 high scores. Next, let me introduce the Q-learning algorithm used in this project. The Q-learning algorithm is implemented in Python in this project, and its implementation can be divided into 6 key parts. The first part is the state space design, which encompasses all the information the agent can understand about the environment. Danger straight, danger right, danger left represents danger in front, right, and left directions. Direction left, direction right, direction up, direction down represents current movement direction. Foot left, foot right, foot up, and foot down represents relative foot direction. The second part is the action space design, which includes the actions the agent can perform. The agent can move in 3 ways: straight ahead, right turn, left turn. The third part is the training process. This diagram shows the overall training flow of the project. Basically, the agent determines movements based on Q values and updates Q values based on rewards. The fourth part is the Q table structure. The Q table in this project is stored using a dictionary where the keys are state tuples and the values are arrays containing 3 action values. This means that the state space and the action space combine to form the basic structure of the Q table. The fifth part is key parameter settings. Alpha, also known as the learning rate, is set to 0.1, which controls the learning speed of new knowledge. Gamma, also known as the discount factor, is set to 0.9, balancing immediate and future rewards. Epsilon, also known as the initial exploration rate, starts at 1.0, indicating completely random exploration. Epsilon min, also known as the minimum exploration rate, is set to 0.01, guaranteeing a minimum probability of exploration. Epsilon decay, also known as the exploration rate decay, is set to 0.995, controlling the transition from exploration to exploitation. The sixth part is core algorithm implementation. The core algorithm can be divided into 2 parts. The first part is the action selection based on the epsilon greedy strategy. The code means that with a probability of epsilon, a random action is selected, or with a probability of 1 minus epsilon, the action with the highest Q value is selected. The exploration rate will decay over the course of training. The second part is Q value update. Here, the core update formula of Q learning is used. Let me explain this. New value is the updated Q value. Old value is the old Q value for the current state and action. Alpha is learning rate, and the gamma is discount factor. Next max is the minimum Q value of all possible actions in the next state. Based on this formula, the agent can learn how to perform corresponding actions by perceiving the environment. Detailed explanations can be found in the GitHub link for this project. That concludes my introduction to this project. Thank you for watching.